so from those information, let's see how this one. The null hypothesis was the assumption that the average was 0. Alternative want to know if it's more than 0 pounds of losing, right? That is the right tail. Right tail test. What we get, the sample mean was what? Sample mean was 3.0 pound of losing. Sample standard deviation. As we discussed already, the standard deviation is from the sample, so that is S. Right? It follows, even though the population, we don't know if it's normal, but the sample size is large enough, right? More than 30, we can use the t-test. I follow the central limit theorem, but use t-test instead. So for the t-test, we're looking for the critical value and the rejection region. Right? The critical value and the rejection region basically is same as last chapter we see before. How to find the critical value is to find the area under the tail and the degree of freedom. Right? In this case, our area of right tail is 1%, which is one tail test. I will go to the t-table, use one tail. And the sample size is 40, so degree of freedom is 39. My degree of freedom is 39, area in one tail, in the right tail basically is 0.01. Therefore we get the t-score, since it's right tail, the t will be positive, in this case 2.426. Right, find out our critical t-test, therefore the region will be set. Right, that is first thing to do to find the critical value. Then we go to the standard deviation of the sample mean. That is sample standard deviation over square root of 40. Right, 4.9 divided by square root of 40. 0.77, I think. Right, and since the standard deviation of the sample is given, we use the t-test. Sample mean was 3.0. The population mean assumption was the diet was not useful. Try to make it 0 and divide it by 0.7476. .872. Why we keep the t into 3 digits decimal? Because the table provided the critical t-score has 3 digits of decimal. Then when we get t, it's better to keep 3 digits of decimal places. Right, then we could shade the right tail of the t-test. The rejection region is the critical t-score of 2.426. That is the region of rejection or rejection region. And we find the t star is 3.872 is bigger than the critical t value, which is falling in the rejection region. Right, therefore, if it's falling in the rejection region, we say reject actual. When we reject the null hypothesis, what we're doing is actually accept the alternative hypothesis. The mean is bigger than 0. So we have, it could be strong, it could be enough. Let's say strong evidence. The mean loss is greater than 0 pounds. Now actually how effective it is. It's greater than 0 pounds just means it's useful. Right? For 1 year, if you just lose 3 pounds, in other words, that is maybe not that useful. Right? For someone maybe eating a little less today could lose maybe 4 or 5 pounds tomorrow. That could happen. But for 1 year, losing just 3 pounds maybe not that very useful for the diet. But actually, at least this question was done here, asking for if it's the mean loss is greater than 0. No, that is greater than 0 from this work we show here. I have enough evidence to support the claim, right, that the mean weight loss is greater than 0 pounds. Right, so that is the question that we can see the wordings provide the sample standard deviation. So from that, we directly know that we need to use t-score. So before we do everything, we find the critical value. We go to the t-test table. There are second column we're using for last chapter, the area in 2 tails. Right, but here we use the area in 1 tail. If it's the right tail test, the critical t-score is positive. If we use the left tail test, the critical t-score will be negative. Right, then the same way we find out the area, we find out degree of freedom, then the intersection of the row and column will be the critical value we're looking for, right? Positive or negative based on the tail. Left or right we're looking for. Then go to the standard deviation of the population mean, of the sample mean. Right, this S over radical n or sigma over radical n before is actually the standard deviation of the sample mean. Right, so whatever the test of z or test of the t is still kind of the z-score, right? Take out the effect of the mean and the standard deviation of the sample mean, right? The sample mean minus the population mean of which is the sample mean, which is the mean of the sample mean divided by standard deviation of the sample mean. We get the value. Then to see if the critical region we get, or rejection region we get from the critical value, actually the t star falls in that or not falls in that. Then we draw the conclusion. let's see the next question. A simple random sample of 9 supermodels has a mean height of 69.9 inches and the height has a standard deviation of 0.84 inches. Oh, it gets 9 supermodels have a mean height of 69.9 inches and the standard deviation of 0.84 inches. Alright, so that again, wording is a little easier. Which the standard deviation is a whole sentence, right, which is from the sample. The height has a mean of 69.9 inches still. The height has a standard deviation of 0.984 inches for those 9 people. Right, then 1% significance level. Test the claim that the supermodel has a height with a mean that is greater than the mean height of women, which is 63.8 inches. Right, the mean height of women for the population is 63.8 inches. Assuming that, well, the height of supermodel is normally distributed. That was given for 9 supermodels, the mean height of 69.9 inches, the standard deviation of height is 0.84 inches. 1% level significant to test that the mean of the height is greater than the mean height of women, which is 63.8 inches, and assume it's normally distributed. So assume normal. That means the condition of center limit theorem holds. And the standard deviation given was the sample standard deviation. So we use the t-test. Null hypothesis, alternative hypothesis. Alternative is a claim to claim that the mean is bigger than 63.8 inches, which the 63.8 was the population mean of the women's height. And assume that, well, the supermodel is nothing different than the population mean of the women. But the height of supermodel itself is normally distributed. We don't know if the mean height of the supermodel is same as the original population mean or could be bigger, right? That's what we're testing on. Sample mean is what, 69.9? Sample standard deviation is 0.84. With sample size 9. And with alpha to be 1%. So what we get is the right tail test still. Right, the right tail test to say it's bigger than. Right, so we get degree of freedom equals 8. Two conditions, right? Degree of freedom is 1 less than the sample size is 8. Area in the right tail is 1%. We get t-value is 2.896. Right, the critical value is positive because it's the right tail test. Right, then we go to find out the standard deviation over radical n. Which is 0.28. Maybe I write a little closer. And then the critical value we found already, we need to find the test statistics. X bar minus mean over S over radical n. Population sample mean found or given was 69.9 inches. Population mean was 63.8 inches. Divided by the standard deviation of the sample mean is 0.28. We find out, well, it's super large, right? That is 6.1 divided by 0.2 will be 21.786. When we draw that, we get critical value is already large, that 2.896. The critical value, right? And it's right tail test, but 721.7 is way bigger. Much bigger, right? 21.7. Right, 2.1, the 21.7 is much bigger than the critical value. Therefore, reject HO, accept HA. The mean is greater than 63.8. Right, so we have very strong evidence. Of course, the words we're using here is very strong because T-crit is too far away from the test statistics, so it's too far away from the critical value. We have very strong evidence. To support the claim that the mean height of supermodel is greater than 63.8 inches. Which is naturally or naturally correct, right? The way they're looking for the supermodel should be satisfy some condition that it should be at least height is above certain level, right? Above certain height, which the mean height of 63.8 of women should be lower than the minimum requirement. Right. Oh, let's see the next question. have weight. A clinical trial was conducted to test the effectiveness of the drugs. The name is zopiclone, right, for treating insomnia in elder subjects. Well, let's assume that the 16 sample values are randomly selected from a normally distributed population who had a mean wake time of 102.8 minutes. If the wake time getting lower, right, then we say the medicine is effective, right? But it takes about like more than almost 2 hours, 1 hour and 40 minutes, more than that for a person to get into sleep. Right, the wake time is still that. Right, after treatment. After treatment with zopiclone, the medicine, right, the 16 subjects had a mean wake time of 98.9 minutes and a standard deviation of 42.3 minutes. So it's like a little different effects here for different people, right? The standard deviation is kind of large. But it is getting a little lower, right? So we try to test the claim after the treatment. We want to test here is after the treatment with zopiclone, subjects have a mean wake time is less than 102.8 minutes and the 5% level of significance. Right, so the first sentence actually telling us nothing just about the test they're doing, right, the clinical trial, what the trial is doing. Right, so 16 sample, simple random sample, mean wake time. The population is normally distributed. The population has a mean wake time of 102.8 minutes. Then after the treatment, the 16 subjects have a mean of 98.8, has a standard deviation of 42.3 minutes. Right, so that's mean and standard deviation I just underlined is for the 16 subjects, which is the sample mean and sample standard deviation. Right, so we want to see after the treatment with opaque clones of jet has mean wake time is less than 102.8 and the 5% level of significance. Right, so actually that's much information provided. We get to the hypothesis. Originally, we know that the population mean was 102.8, but after treatment, it may be still 102.8, or it may be smaller than 102.8 minutes. So this is our left tail test. Our left tail test. What's also known is the sample mean was actually getting smaller with sample standard deviation of 42.3, which is pretty large. Sample size is 16, alpha is 5%. We'll get sample mean, sample standard deviation, sample size, and alpha for things, right? So sample size is 16, therefore degree of freedom is 15. Area in the left tail is 5%, so we go to the table to find 5% and 15, intersect with 1.753. But since it is the left tail test, our critical value will be a negative 1.753. Right? The critical value should be negative since it is left tail test. Then the standard deviation over radical n, that is 42.3 divided by square root of 16. It's about 10.575. Then the test statistics. Sample mean is 98.9 minus 102.8. The difference is like 3.9, right? Divided by 10.575. That will get negative only 0.369. Or keep 3 digits decimal, we get only that. Right, so when we compare, draw the left tail test, right? The density curve for the t-test, t-distribution of degree of freedom of 15, we get negative 1.7. 753 as the critical t-value, and the rejection region we get only the t-star, negative 0.369 over here, right? That is the t-star, which is out of the rejection region. So when it's out of the rejection region, that is the case we're not able to reject the original hypothesis, therefore we can only accept the null hypothesis. The mean is still 102.8 minutes. That is the case that, well, the medicine or the drug clone actually doesn't help the insomnia. There is no evidence to support the claim that the mean wake time is less than 102.8 minutes. Right, the mean wake time is remain on, hence the Zope clone is not effective. Cannot help us, right? It's not effective to insomnia. It cannot help us to lower the wake time. Right, so that is everything of chapter 8. What we see was just the hypothesis testing for population mean. In the case standard deviation of population, in other words, sigma is given, that it follows the z-score, right? Of course, the central limit theorem's condition should be satisfied. Right? Then we use z-score, then we use p-value method. Right? If the case that the standard deviation of the population is not given, but we know the sample standard deviation, then we can use the t-test. Finding the critical value, use the traditional method, critical region or rejection region, critical value false out, that's fail to reject, false in, that's reject for the null hypothesis. Then we make a decision and write down the conclusion what the entire steps, what they are mean. Right, so that is everything for the chapter, and that is everything for our course. Alright, so this is the last video we have.